Okay, welcome back. Now the demo I'm going to do is also a really good physics problem. There's a lot of good physics involved in it. It involves rolling motion and also the concept of rotation about a pivot point, right? So the question I'm going to ask is, what is the minimum velocity the ball must have in order to not jump the ramp? So you can see here from this problem what this looks like. So I have here two spherical balls, right? Different diameters, and then the question I'm going to ask is I'm going to roll them here along this horizontal plane, and then you see how it's rolling. It's coming and rolling nicely into this inclined plane and rolling down. The angle of the inclined plane is about 3 degrees. 3 degrees. So the question I'm going to ask is, what should be the maximum velocity of the ball in order for when it comes here, in order for it not to jump, not to skip like this. I want it to come nicely and roll, right? So if I go slow, you see, it never loses contact with the surface of the material. It just kind of rolls nicely, right? But if I do fast, you see, what happened when I did fast is it came here, and for a while you didn't hear the sound of the rolling, right? It kind of jumped until it landed somewhere here, and then you heard the sound of the rolling. Now this one is a smaller radius, right? Let's try that one. You see, that one didn't jump because it was going so slow. It came to the surface and it just rolled nicely. Now let me do fast. Okay, over here it kind of jumped, right, until it landed somewhere about here. Then it started rolling. So if I don't want it to jump at all, what should be the maximum velocity of the incoming spherical ball, right? Something like this, okay? And then this one has an angle of theta, right? So let's consider what happens to the ball when it gets to the edge of that ramp, right? Right at that location. What happens to the ball? What is the dynamics and the physics of what is going on? Well, this is kind of similar to the topic that we have when we do rotational motion, and we say, imagine taking a rod, right, pivoting it about the end, right? Then let's see what happens to that rod, right? As it is starting to fall, right, what is the dynamics of that? So it might be good to do a quick review of that. So as it is falling, right, like that, let's call this angle theta. As it is falling, what's going to be the velocity of different points along the rod? Okay, so we say the initial potential energy of the rod when it is up on the top is equal to the final kinetic energy, half I omega squared, right? This one has only rotational motion, right, about the pivot point. So mgh equals half I omega squared. So then we use the moment of inertia about the end of a rod, which is 1/3 ml squared. 1/3 ml squared omega squared. You can use a certain reference point as your point to measure potential energy from. So if you use the bottom of the rod, xy, so then h, you could say this is h initial, and then add here mgh final. Right? You could do that way, or you could use the center of mass of the object as your reference point. Either way. So let's say if you use the bottom pivot point, so then what's going to happen? mgh initial, h initial is going to be the center of mass is right here. So the h initial is just going to be L/2. Right? And then over here, what's going to happen? H final, mgh final. So this is going to be L/2, right? And then if this is theta, this one here is going to be L/2 cosine theta, right? Because the theta is measured from the vertical. I'm measuring it from the vertical. So then if you make a triangle like this, where this is the center of mass, goes like this. So this is going to be L/2. This is theta. This is L/2 cosine theta, right? So then I'm going to say H final equals L/2 cosine theta, right? Then I'm going to cancel the m's, okay? So then what's going to happen, right? And then the 6 can go over there and then make this 3GL, right? 1 minus cosine theta over L squared equals omega squared. Then I can take square root of that. That will give me the omega, right? So it depends, of course, how much it has fallen. If the final angle theta is 90, what happens? If the final angle theta is 90, then it looks like this. It'd be theta is 90. So then cosine of 90 will be 0, right? Which in this case, then you'll just get one of the L's cancels. So you just get a square root of 3g over L, and then cosine 90 will be 0, so this will disappear. Okay? Once you calculate the omega of the rod, you can calculate the center of mass velocity by just multiplying it by r omega, right? So we've done this problem, and I have a video on how to do these kinds of things, quite a lot of videos. So the physics of this will be pretty similar to that. We're going to say when the rolling sphere approaches to the edge, it already is rotating. So it's a little bit different than this because it already has rotational energy, right? That's omega initial. On top of that, when it gets to the edge, it's going to also pivot about the edge for some point until it has rotated through an angle theta, which will equal to the same angle as the angle of inclination. After that, it will keep rolling, right? So this theta and this theta are actually the same, but the difference is that this theta is changing. As it's rotating, it's increasing, right? So here, and let's analyze the center of mass, right? After it has rotated about the pivot point through some angle, let's say like this, the center of mass is here. And then I'm going to say this is going to be the angle alpha. Angle alpha, and where angle alpha can be any angle, and as it's rotating about the pivot point, that angle is increasing, and the maximum of the alpha will be theta, the same as the angle of inclination of the incline, right? Because the incline will not permit alpha to be larger than that, right? So then the setup will look similar to this. I have the initial potential energy, mgh initial, plus the initial, except I have to add initial kinetic energy here. Half I omega initial squared, given by the initial velocity that it's coming in, right? The V center of mass, this is V initial, right? Depending on its initial velocity, it has a certain rotational kinetic energy. Then I have here mgh final plus half I omega squared final, okay? So let's derive a general equation for the final omega as a function of how much it has pivoted about the pivot point and its initial kinetic energy. So here I have mg. What is the initial h? In this case, I'm measuring from, let's say, the pivot point is the ground right here. So the initial h is going to be the radius of the ball, right? So mgr. What's the moment of inertia about the pivot point, right? So this is similar to the rod. For the rod, it's 1/3 ml squared, right? For the pivot point of a solid sphere, what is this? This is solid sphere. Okay? So then it's going to be the moment of inertia of a sphere with respect to the center is 2/5 mr squared, right? So then since it's pivoting about the end, I add on top of that, I say moment of inertia about the end is equal to the moment of inertia about the center of mass plus the shift amount from there to there is mr squared, right? Mr squared with respect to the end. So then I put that here, 7/5 mr squared, omega initial squared. So that's the moment of inertia here. Then here I have mg h final. H final will be same that I had here, similar. It'll be r cosine of alpha, right? R, and then cosine of alpha will be the vertical component of it. So r cosine alpha. Okay? So then I'm going to say, then I add to this 1/2. The moment of inertia, I put it again, 7/5 mr squared, omega final squared. tenths. Now, r times omega initial is going to be the initial velocity of the center of mass, right? V center of mass equals r omega initial. Right, so then I could put here VCM squared. And so I can just call that the V initial of the sphere. So GR plus 7/10 V initial squared is equal to GR cosine alpha plus 7/10 R squared omega final squared. Okay? So then what is happening? As the thing is falling more and more, what's happening to the alpha? The angle alpha is increasing, right? When the angle alpha increases, what happens? Cosine of an angle, when the angle increases, cosine of the angle decreases, right? So this term decreases. This is the initial kinetic energy. This is the initial potential energy. They're constant. So as this term is decreasing, the omega is increasing, right? Omega is increasing, and that makes sense. So it's starting to rotate faster and faster and faster, right? The greatest that the omega will get, when the angle alpha equals to theta, right? So when the angle alpha gets to theta, right, that means the sphere has rotated through the same angle as the inclined plane, and now it's ready to start rolling down the inclined plane. So alpha becomes equal to theta, right? So that means this is the smallest that this term will get, and that's the fastest that the omega will get. Now we're going to analyze circular motion, the concept of circular motion. Okay? So when something is going around a circle, what happens? Okay? Previously I've done this problem, and you can look at my videos. I've done a sphere rolling on a sphere like this, and I've calculated at what position does the top sphere lose contact with the bottom sphere, right? So this kind of utilizes this concept too. So then how did I solve that? I said this is the normal force, this is the mg, and then this is going to be mg cosine theta, right? So then I said mg cosine theta minus n is equal to mv squared over r, right? So for that problem, the way that I did it, I said let the n be equal to 0, and when n equals 0, this equals this, and that's the greatest velocity that the ball can have, the rolling ball on top of another sphere. So you can watch the video on that and show and see how I solved that. This is going to be similar. So then I'm going to say, as this thing is going this way, as it's falling, it's also making like a circular motion, right? So then look at what is happening as it's turning. You see, like this. The initial center of mass is like that. Then it's turning like this. You see? So this is the normal force. This is mg, right? So then we're going to have here mg cos theta. Mg cos theta is this component of the force, and it's turning and making a circular motion, right? So we're going to have here mg cos theta minus n is equal to mv squared over r, where this is v final, right? V final of the center of mass. V final of the center of mass. So now, if I set the normal force equal to 0, what do I get? When the n is equal to 0, that tells me that's the greatest final velocity that the center of mass can have. The greatest final velocity is what? mg cosine theta is equal to mv final max. That's the maximum velocity that it can have. Now in the case of the rolling sphere, what happened? The rolling sphere was coming down and it was gaining velocity. At a certain point, when the v is equal to v final max, it left the bottom sphere. Now here's what is happening. Depending on its initial velocity that it has, and depending on the angle, it's starting to gain velocity, right? You don't want to gain too much velocity, because if you supersede this velocity, the normal force becomes 0, and it actually leaves the ramp. So it kind of gets airborne like that, then comes back and hits the ramp somewhere here. We don't want it to leave the ramp, right? So in order for it not to leave the ramp, the greatest velocity of the center of mass, VCM, the greatest value of that should equal to this value, the Vmax. Okay? So then we're going to say here, what is Vmax? Okay, so V final max is gonna be what? M cancel. So it's gonna be RG cosine theta square root. Okay. Well, look at this. R omega final is V center of mass. That's V final, right? So I can replace this by V final squared. I want this final velocity to be no larger than that one, right? So then I can put here V final, replace it with this, and then square that, right? V initial squared. If I multiply everything by 10, this will cancel this, and that will make it this 10. So I'll make here 17 GR cosine theta minus, and then this will be 10 GR, right? And then divide everything by 7, I'll have 1/7, right? And then this is the initial squared. Okay, can I factor out anything? I have GR over 7, 17's cosine theta minus 10. That is the maximum velocity that V initial can have, because if it's any faster than that, then the final velocity will be greater than the GR cosine theta, and it will leave the surface. Okay, so it's V initial max. The angle was 3 degrees, so we have GR over 7. So 17 cosine of 3 minus 10. And then, of course, depending on what size ball we have, it has a radius of about 3 millimeters. So it would be for the smaller ball, right? Now, the larger ball, you can actually go faster because its radius is bigger, right? So the radius is bigger. It's about it's about double the size. It's going to be, if it's double the radius, it's going to be about rad 2 times more than this that it can go. Okay, so times, so that's going to give you 0.242. So the bigger ball can go about 0.24 meters per second before it leaves the ramp, whereas the smaller ball leaves the ramp quicker, right? So what will happen as the angle of inclination gets bigger and bigger and bigger? What's going to happen? Okay, if the angle of inclination theta is equal to 0, what's going to happen? GR over 7, 17 cosine of 0 is going to be what? That's just 17 minus 10. So 17 minus 10 is 7. So it's going to be square root of GR. So that means basically that's the same thing as the maximum velocity that a roller coaster can have. So imagine there was a roller coaster like this. All right, the roller coaster was coming down, and at the top, the roller coaster was going in a circle like this, right? And we derived the maximum velocity that a roller coaster can have so that it doesn't leave the ramp like this, right? So it becomes almost a regular circular motion problem. What's the maximum velocity that a roller coaster can have? Square root of GR. So this kind of proves that our equation was right. If this whole thing was just flat without a ramp and it was on top of a circular ride of radius of curvature of r, right? If it was just a regular roller coaster ride, the maximum speed that it could have was square root of GR, so that's the result that we got. Now we've added a different component to it, this ramp concept, right? So therefore the equation is making sense. As the angle gets bigger and bigger and bigger, right, what's going to happen? Cosine theta. What's the maximum angle that this can be, right? Okay, so 17 cosine of 10. We don't want this to ever be 0, right? As the angle is getting bigger, cosine of 90 is going to be what? That's going to be cosine 90 is going to be 0, and you're going to have negative 10 here. You can't have that. That means you can't have like this, a flat horizontal plane, and then another one that's vertically down, and then the ball come and stay on the ramp, right? That's why the theta can never be 90 degrees, because it's going to just come and then it's going to fall, of course, right? So what's the greatest angle that theta can be? Set this thing equal to 0, right? 17 cosine of theta minus 10 equals 0. Cosine of theta is 10/17. Saying is that no matter how slow this sphere goes, right? No matter how slow the sphere goes, if this angle was greater than 54 degrees, right? If it's any greater than 54, like let's say it's 60 degrees, it's going to go like this, right? And then of course it's going to just fall off here, no matter how slow it's going. The greatest the angle can be is 54. Less than 54, maybe if it's 45 degrees, You could go a little bit faster and still make contact with the inclined plane. But if it's 3 degrees, it can go as fast as 0.17, and for the bigger sphere, it can go 0.24 meters per second. Okay, so now you can see how the V initial depends on the angle and the radius of the ball, and then you can see the limits of the answer. If the angle theta is 0, the maximum speed is square root of gr, right? And as the angle gets bigger and bigger, it becomes harder and harder to achieve this until you get to 54 degrees, and 54 degrees is the greatest angle that you can still achieve this. Thank you very much.